TV from Cambridge Institute of Technology. Today's session we are going to discuss about plane trusses and stiffness matrix of the plane truss element. Okay. Before going to know the analysis of trusses, let me first explain what is truss. Truss is a skeletal structural type of member which is an assemblage of number of bars. Okay, it is assemblage of slender bars which is going to be connected at their ends, or it is also fastened. So by the means of pins, balls, or by socket joints, and also as the hinges. A truss element is a straight bar having a arbitrary cross section which can deform only in axial direction, as it is subjected to the axial forces similar to the bars. Only it is one-dimensional case, only in one axis, that is along the axial direction the load is applied, only in the along the axial direction the deformation takes place. So thus the truss elements is also termed as bar elements. Based upon the number of degrees of freedom, the trusses are categorized as planar trusses and space trusses. The planar trusses, which is having a two components in xy direction, along with xy direction there will be a two nodal displacements as the forces applied at two directions at each node, so that these structural planar trusses lies on the plane. Okay. So as it is laying on the plane, the load also loaded in the same plane only in planar trusses. As we considering a space trusses, in the space trusses there will be three components, that is in x, y, z directions. So it is having a three directions. In three directions there will be a nodal displacements and forces at each node. So that this is a case of three-dimensional problems. At three-dimensional analysis we can carry it out because of there is a 3 degrees of freedom. So these members is not lying on the same plane because there is one more direction in the z direction, so that it is not laying on the plane, and also the load is not loaded on the same plane. So now just consider a few examples of truss applications. Okay. So there are so many applications of truss in the structural engineering. Now just take examples for the plane truss and space truss. In the plane truss problems, the structure will be like this, and which is having a nodes, like number of nodes it is going to be consisting, and each node there will be a 2 degrees of freedom that we can analyze in x direction and y direction as 2 degrees of freedom. Okay. So similarly, if you take a space truss, in the space truss there will be 3 degrees of freedom. So along with x and y and z direction, we can able to do the analysis to get the nodal displacements at each node. So the structures will be like this for the space truss and plane truss. Similar way, there are so many types of structures which is going to be exist in the engineering. Now two more examples I have taken: a trussed bridge, okay, and also braced frame. We are going to consider as a space trusses. These are the few application examples for the plane truss and space truss. Okay, now here you can see a engineering applications. Okay, so there is a steel bridge here which is consisting of or assemblage of number of bars, and it is connected by the means of pins. Okay, here, and also you can able to see here. So here this structures, it is assemblage of number of straight bars. Okay, so the structure connected by the straight bars, so that this is also termed as a bar elements. Okay, this bar elements is connected at this particular point through pins. Okay, then only the load is taken by these pins at that particular point or node only, so that whatever the load, it is going to be considered only at nodes for the truss members. Okay, these are all the few examples for the truss applications. Now, a plane stresses. Okay, we have how we need to analyze. Okay, the analysis of plane stress. To discuss, I have taken a typical two-dimensional plane stress as shown in figure, which comprises of two force members. Okay, so each node there will be 2 degrees of freedom, so that it is going to be undergoes two nodal displacement, that is Q1 and Q2, due to two force members. Okay, each direction, each coordinates, it is going to be having a force vectors. Due to that force vector at that particular direction, there will be a nodal displacements, okay, that we are going to represent here. So a typical two-dimensional case which consisting of 8 nodes along with the 13 elements. Okay. The node number 1 is completely constant here and node number 5 is completely constant here. So at node number 2, 3, 4 is load is applied as P1, P2, P3. Okay. At node number 1, there is a 2 degrees of freedom and also there are 2 force vectors. Okay. So along with the x and y direction, in the x direction nodal displacement is Q1, y direction nodal displacement is Q2. Similarly, at node number 2, Q3, Q4. Similarly, at node number 3, Q5, Q6. At node number 4, Q7, Q8. At node number 5, Q9, Q10. Similarly, it goes on up to 8 nodes. This way, the analysis of truss members we are going to do as it is considering as a finite element model. Okay. So before going to do the analysis, just we are going to write it that we are going to call it as a finite element model. That modeling is nothing but a discretization. In this discretization, we can able to get elements and nodes. Okay. So this is a typical example for a plane truss. Now consider the stiffness matrix for the truss element. So we know that there are two coordinate systems. One is local coordinate system, another one is global coordinate system. Now you can see the figure here. So the element which is having node number 1, node number 2 along the x direction, x dash direction, which represents the local coordinate system, and here x and y represent the global coordinate system. So in this x dash direction, which is having at node number 1 degrees of freedom, node number 2 at 1 degrees of freedom, which means in local coordinate system, which is having only one direction, that is x dash direction, so that at node number 1, node number 2, each node which is having only 1 degrees of freedom. Similarly, if you take a global coordinate system, each node there will be a two coordinates, that is x and y. Okay, as you can see here. Okay, so that at each node there will be a 2 degrees of freedom. Now, if you want to write a nodal displacement for this particular element at node number 1 and node number 2 in local and global coordinate system, so you can see here. Okay, so the nodal displacements vectors, it is represented by the q. Okay, q dash it is represents in local coordinate system, q it represents in global coordinate system. So q dash, which is equal to in local coordinate system at each node only 1 degrees of freedom, so that there will be a possibility of only having a one nodal displacement at node number 1 and also one more displacement at node number 2, so that for two nodes only two nodal displacement, that is q1 dash and q2 dash. Okay. Similarly, same thing if you want to write in global coordinate system. So at each node we have 2 degrees of freedom in global coordinate system in x and y direction, so that there will be a 4 nodal displacement. At each node 2 nodal displacement. First node q1, q2 are the nodal displacements, and second node q3, q4 are the nodal displacements. So this is how we are going to write the nodal displacements in local and global coordinate system. Now we need to know the relationship between the two coordinate system. Okay, by using this relationship, okay, then we can able to find out the simultaneous equation. Okay, then you can see here, consider a deformed stress member. Okay, this is the in local coordinate system, it is in global coordinate system. Here the element which is having node number 1, node number 2 in local coordinate system. Okay, which is the whatever the displacement represented by q1 dash at node number 1, at node number 2 q2 dash. Okay, so as it is deforming, it is going to be shifted to this. Okay, so that whatever the displacement in x and y direction for the global coordinate system, and also q1 dash q2 dash in local coordinate system, how it is going to be expressed and how it is going to be correlate, that we are going to discuss now. Just see here. So this is before deformation and this is after deformation. So after deformation, it is having a it is shifted from here to here. Okay, so that it is in the x direction, the displacement is q1, and y direction displacement is q2. And total, if it is taking only in one coordinate system, that is in local coordinate system, from here to here it is displacing, that is as you are drawing the dotted lines here. So the total displacement is q1 dash. So as whatever the displacement, it is in local and global coordinate system, it is equal, because hence it is independent from the coordinate system, so that q1 dash which will be equal to q1 plus q2. Okay, whatever the displacement, nodal displacement in local coordinate system must be equal to the displacement in global coordinate system. Okay, so to write that, now see q1 dash in local coordinate system, which is equal to here. So it is having xy, so that there will be inclination as it is having a displacement. So x and y plane, if it is having, then there will be a inclination. That is due to that inclination, what are the total length of this particular nodal displacements, we need to find it. Okay, now see this q1 dash in local coordinate system must be equal to the whatever the total displacement of no global coordinate system. Okay, now if you take this triangular, this geometry, which gives, this is, take it as adjacent, and this is hypotenuse, and this is as opposite. Okay, so as you taking this length to find this length adjacent, okay, taking cos theta, which is equal to adjacent by hypotenuse, so that adjacent, which is equal to q1, this is hypotenuse, q1 into cos theta, so which gives the adjacent length is nothing but q1 cos theta. Similarly, as you taking this uh, nodal displacements q2, okay, as you are writing the triangle here, okay, so from that uh, triangle we can able to find out. Okay, so it is opposite if we take, okay, then sin theta, which is equal to opposite by hypotenuse, then whatever the opposite direction length here, opposite direction length, which is equal to the q2 sin theta, that is hypotenuse into sin theta. So this overall length of that particular displacement deformed element is nothing but q1 cos theta plus q1 q2 sin theta in global coordinate system. Okay, then in the local coordinate system it is q1 dash, so that q1 dash, which is equal to q1 cos theta plus q2 sin theta. Similar way at node number 2 also we are going to write the total displacement is q2 dash in local coordinate system. Similarly, as you taking the triangles here, okay, we can able to find out for Q3, Q4, as it is taking Q3 cos theta plus Q4 sin theta. Displacements. Now consider a direction cosine. Okay, just we are going to replace this theta. Okay, so to avoid this theta, so we are going to use the direction cosine. In place of cos theta, we are going to use L. In place of sin theta, we are going to use M. Okay, so that L, which is equal to cos theta, M, which is equal to sin theta. So the relation between the local and global coordinate system for the nodal displacement is given by now q1 dash, which is equal to q1L plus q2M. Similarly, at node number 2, q2 dash, which is equal to q3L plus q4M. Okay, so now this simultaneous equations which give the relation between local and global coordinate system in terms of direction cosines. Okay, now again this simultaneous equation, if you write in the matrix form, then you can also write like this. Okay, q1 dash q2 dash, which is equal to, here this multiplication factor must be equal to this simultaneous equation, so that if you write in matrix form, then this becomes LM00. Okay, if you, this row multiplication of this column, which is this equation, and this row multiplication of this column, which is this values. Okay, so that we are going to write it in matrix form. Okay, now again this you can also write it in q dash, which is equal to L into q. Then the nodal displacements in local coordinate system will be equal to q dash, which is equal to this matrix, it becomes the transformation matrix, and this becomes the global nodal displacements. Okay, so that q dash, which is equal to L into q, where L is the rectangular matrix, or also call it as a transformation matrix, and q will be the nodal displacements in global coordinate system. Now, for evaluating the L and M values, as you considering the L and M values in this particular equation in the transformation matrix, we need to obtain the direction cosine values. Okay, to obtain this direction cosine values, just consider the truss element. Okay, at node number 1, at whatever the coordination values is x1 and y1, at node number 2 x2 y2. Okay, then as you draw extending these lines, okay, so this to write it as a triangle. Okay, so this whatever length, which is nothing but x2 minus x1, because x2 minus x1, this length equal to x2 minus x1, and this whatever the vertical length, which is equal to y2 minus y1. In horizontal in the x direction, vertically in y direction. Okay, now L, which is equal to cos theta, which is equal to adjacent by hypotenuse. Okay, just if you consider this is as adjacent and this is as hypotenuse, then cos theta which is equal to x2 minus x1 by LE. Similarly, considering m which is equal to sin theta if you consider this is becomes our opposite and this becomes the hypotenuse, then sin theta which is equal to y2 minus y1 divided by LE. Okay, then LE which is equal to mean effective length. Okay, as per the Pythagoras theorem. Okay, so what it does Pythagoras theorem, c square which is equal to a square plus b square. Okay, so if it is length of the element is c square and adjacent and opposite as take it as a square and b square, then which gives c square which is equal to a square plus b square, then c which is equal to square root of a square plus b square. Similarly, LE which is equal to square root of here this square. Okay, x2 minus x1 whole square plus y2 minus y1 whole square. Okay, this gives the effective element length. Then to obtain the elemental stiffness matrix, now the truss element, this truss element consider in local coordinate system, and if you consider this truss element in local coordinate system, that will be equal to the bar. Okay, so if you see the bar in local coordinate system will be equal to the as a will be equal to the truss element. Okay, now the elemental stiffness matrix for truss element in local coordinate, we can write it k truss which is equal to a by LE 1 minus 1 minus 1 1. Okay, so the internal strain energy for the truss element in local coordinate system. Okay, the strain energy equation, general equation, we can write it here, UE dash which is equal to 1 by 2 Q dash transpose K dash truss Q dash. Okay, this is in local coordinate system, the strain energy in local coordinate system for the truss element. Okay, from equation number 1 we know, okay, the relation between the local and global coordinate system for the nodal displacements which is equal to Q1 dash which is Q1 dash which is equal to L into Q. Okay, so substituting this Q1 dash values in this particular strain energy equation, which gives UE dash which is equal to 1 by 2 L Q transpose K dash truss L into Q. Okay, now just again this is rewriting UE dash which is equal to 1 by 2 Q dash, okay, L transpose K truss K dash truss L into Q. Now again write the strain energy for the truss element in global coordinate system. Okay, if you write in global coordinate system, then UU which is equal to 1 by 2 Q transpose K truss Q. Okay, now thus strain energy for if you write in global coordinate system and local coordinate system, okay, that will be same because here the strain energy is independent of coordinate system. Okay, the internal strain energy is independent of the coordinate system, so that the strain energy in local coordinate system will be equal to the global coordinate system. As comparing both, okay, this local coordinate system strain energy and global coordinate system strain energy, as comparing this both, in k truss this term will be equal to overall this term, so that k truss which is equal to L transpose K dash truss L. Okay, then L is a transformation matrix. That matrix values you can write that L which is equal to L m 0 0 0 0 L m, and K dash truss it is equal to the elemental stiffness matrix for the bar and truss element in local coordinate system. So AE divided by LE 1 minus 1 minus 1 1. Then L which is equal to again the transformation matrix LM 0 0 0 LM. Now this both matrices going to be multiplied. Okay, after multiplication we are going to get the matrix like this. Okay, just this row into this column which gives L, and this row into this column gives M, this row into this column which gives minus L, this row into this column gives minus M. Similarly from the second row, okay, minus 1 and 1, this row going to be multiplied with this which gives minus L, this row in this column minus M, and this row into third column gives L, this row into fourth column gives M. Again this column matrix and this matrix going to be multiplied. Okay, take it AE by LE out as it is. Okay, then multiplying this both matrix, okay, we are going to get final equation, the final matrix for the truss element like this. Okay, just you can see here the first row into this column, again first row into this column, this row into this column, this row into this column gives the values like this. Just one row I am going to show you. So L, this row into this column which gives L square, again this row into this column which gives LM, and again this first row into third column which gives minus L square, again first row into fourth column which gives minus Lm. Similarly, second row into first column which gives Lm. Similarly, second row into second column which gives m square. Similarly, second row into third column which gives minus Lm. Similarly, second row into fourth column which gives minus m square. Okay, similar way we are going to do it matrix multiplication for third row and fourth row. Okay, then finally we are going to get the truss elemental stiffness matrix, okay, which is equal to AE by LE, L square Lm minus L square minus Lm, Lm m square minus Lm minus m square minus L square minus Lm, L square Lm minus Lm minus m square Lm m square. This is the elemental stiffness matrix for the truss element. Now, how to calculate stress? How to obtain the stress equations for the truss element? Okay, just consider normal stress or from the Young's law, E which is equal to sigma by epsilon, then sigma which is equal to E into epsilon. Epsilon is nothing but just 10 here, that you can write it E into Q dash in local coordinate system. Okay, now B is the strain matrix and Q dash is the nodal displacements in local coordinates. Okay, again here Q dash, the relation in local coordinates to global coordinate system for the nodal displacements is given by Q dash which is equal to L into Q. In place of Q dash you can write L into Q. Okay, then the equation becomes sigma which is equal to E B L into Q. Okay, then expanding B and L, that just substituting the values for the equations of B and L. B is strain matrix which is given by 1 by L minus L minus 1 1, and L is the transformation matrix which is given by Lm 0 0 0 0 Lm, and Q is nodal displacements in global coordinate system, that is Q1 Q2 Q3 Q4. Okay, for the two nodes, then sigma which is equal to E by L, just this whatever the transformation matrix, it is going to be multiplied with this matrix. Okay, then it gives this row into this column gives minus L, this row into this column which gives minus M, this row into this column which gives L, and this row into this column gives M. Then Q1 Q2 Q3 Q4, this is the final stress equation for the truss element. Okay, so this way we can able to obtain the truss equation for truss element. Okay,